good afternoon, everyone. Welcome to the public forum at Group Exhibit Hydrogen Fuel Cells and Batteries. For those in the audience, please feel free to come and join us, grab a tea, grab a coffee, and enjoy the next 20 minutes. I will be speaking about Sustainable Innovations business. I will be speaking with President of Sustainable Innovations. Please welcome Trent Molter to the stage. Thank you for joining me.
Thank you, Roxanne.
So, for those who may not be aware, Trent has a very interesting background within this industry, so I'm going to get him to share a bit about himself with you before moving into the company and their current technology.
Okay, great. So my background is actually in chemical engineering and materials science. I started my career working for United Technologies at a company called Hamilton Standard. Hamilton Standard's in the aerospace industry. They made at the time propellers, and I worked in the group that made spacesuits for NASA. And shortly after I joined, I was asked if I'd be interested in working on fuel cells. And at the time, hardly anybody had heard about fuel cells, and I actually asked my boss, well, what's a fuel cell? My boss said, well, I don't really know. I think it's some kind of battery or something. This was in the early to mid 1980s. It turns out that the company was buying a business from GE that had been involved in fuel cell development. So I had the opportunity to go up to the company in the Boston area that was involved in this development to learn the technology and then to transfer the business back to Connecticut in the US where I was. And I worked there for about 13 years on various aspects of the technology at the time. It was a lot of fun. I got a lot of great experience. And then at the end of my 13 years, started working with a number of folks interested in commercializing the technology. We had been doing work on water electrolysis and decided to form a company called Proton Energy Systems. You might recognize the company now as Proton Onsite. So at Proton, we developed a line of water electrolysis systems, and that line has been very successful to this point in time.
And what was the initiative to start Sustainable Innovations, and how did that come about?
Yeah, so I had left Proton about 3 years after the IPO in 2000 to do something kind of crazy, and that's to go work on a PhD. It's something I had always wanted to do. So as an old guy, I went back to school, but as I was finishing my PhD, I started thinking about all the different ideas that I had prior to starting Proton, and started thinking about sort of how to commercialize these various ideas, and those are the ideas that made up the basis for Sustainable Innovations. So I actually started the company while I was still a student, and actually began the company literally in my garage, and started working on a number of R&D projects that formed the basis of the company.
So how long has the company been around, and what is your primary technology that you're involved with?
So the company was started in about 2007. We had developed a flexible electrochemical cell architecture that could be applied to a wide variety of applications. The idea was to develop this flexible electrochemical cell that could be applied to applications that were very investable. At the time, I recognized that there were many people involved in PEM fuel cells. There were also many people involved in PEM electrolysis, and my background was in PEM itself. So we started looking for what I call the white space, the areas where others were not participating, and these areas that I thought were investable at the time. So we got involved in things like hydrogen recycling. We got involved in energy storage, and also conversion of waste CO2 to organic products. These are things that the world seemed to care about, and that we had technology that was very applicable to.
Can you kind of walk us through how this technology works? Because it's kind of interesting that you take one technology and it's applied to these 4 different kind of processes and applications. So how does that work?
Yeah, so we've developed this electrochemical cell architecture that's expandable. It can be expanded to very large sizes. In fact, we've we had an important press release this week that talks about that. We've developed this architecture that, ordinarily when people develop PEM cells, they have great difficulty expanding this cell size to very large format sizes because of manufacturing constraints. It's very difficult to scale hardware to large sizes reliably because of the tolerances of the mechanical parts in the assembly. We've come up with a design that allows us to expand laterally in the active area of the cell that allows us to create very large format cells and also to be able to operate at multiple pressures. We've gone up to 350 bar and higher with our electrochemical cell architecture. We've also been able to design this cell so that it can incorporate multiple chemistries, and that provides the basis for our architecture that allows us to operate in these various modes.
When you say different types of chemistries, what are you referring to, and why is that important? What are these used for?
Yeah, so I'll talk about the different product areas and the different chemistries involved in the different product areas, and that may take a couple of minutes to go through. The first product area really is electrochemical recycling of hydrogen. That's sort of the first target area that we're focused on. So what we can do is we can take waste gases from different industrial processes, for example, heat treating of metals, silicon wafer processing, processing of glasses, and things like that. So often these processes utilize hydrogen as a reducing fluid, and they have an exhaust of hydrogen and other fluids coming off of them. We can take that waste fluid, which might have CO2 in it, might have water vapor, might have CO in it, and we can use this electrochemical process to strip out the hydrogen, purify it, and then send it back to the feed stream of the process so that the end user doesn't have to buy new hydrogen from the process. So that's one application that we're talking about.
And who would typically be the end user of that? And, how does that benefit them? Like, how does that work in terms of that end user?
So for a heat treater, that might cut down on their hydrogen usage by, say, 90%, let's say. So instead of buying new hydrogen, they might eliminate, say, 90% of their hydrogen usage. Or their other opportunity might be to purchase an electrolyzer to generate the gas on site. In the case of this particular unit, the device in and of itself would be much simpler than an electrolysis system in that there's no oxygen circulation loop within the system itself, and therefore many of the components can be eliminated from the system. Therefore, the end price of the unit will be a lot less, and the power required to operate it would be significantly less.
Okay, and in terms of the other applications, how does that work? You mentioned there was 4. Still trying to wrap my head around that and how all the technical aspects of that.
So we can take the same product architecture using hydrogen, and instead of simply purifying, we can also compress the hydrogen. We simply pump the hydrogen across the membrane, and if you're pumping into let's say a fixed volume, a sealed container, you can electrochemically compress that hydrogen. And again, we've gone up to 350 bar and higher with this device, and it can be by far one of the most efficient ways to compress hydrogen. There are no moving parts in the system. There are no dynamic seals. There's nothing to wear out in the system, and it makes for a very elegant way to do the compression of the system. The third application would be to take the same flexible hardware, and in our case, we're using hydrogen and bromine as the working fluids. That in and of itself makes for a flow battery system. That provides a very efficient means of energy storage, and we're actually doing some development work on that with a number of partners to create a system that we've measured at the bus bar being about 90+% efficient. In an all-up system, we expect that to be about 75 to 80% efficient. And that's a big deal.
What sort of project is this, and who, can you say who you're working with in terms of this?
Sure, that project is funded by the Byrd Foundation. It's also funded by NYSERDA. The Byrd Foundation is a joint U.S.-Israeli collaborative, and the reason the Israelis are interested in it is Israel is actually the largest producer of bromine, which is one of the primary fluids that we use in the process. We've got a formal partnership with a company called ICL Israel Chemicals Limited. They are the world's largest producer of bromine, and they really care a lot about moving this technology forward, and have helped us enormously in the process.
Great. So in terms of the energy storage, with the bromine, that's kind of like for flow battery?
Yeah, it is.
And how does that work?
Yeah, so it's an interesting process. We'll take a chemical called hydrobromic acid, HBr. We'll feed it to this electrochemical cell and take in power, maybe from renewables, feed the power to the cell, and the HBr is electrolyzed at a much lower voltage than you perform water electrolysis. You perform water electrolysis at like 1.5 volts. The bromine is, the HBr is electrolyzed at about 1 volt. And when you do that, you split the HBr into hydrogen and bromine. The bromine is a liquid, and so it's stored in a simple plastic tank. The hydrogen is stored conventionally in pressurized tankage, and that's how you store the fluids. When power is not available to you, you reverse the process, you feed it back to the cell, and you generate electricity. That process, again, is very efficient, and the fluids in and of themselves are actually very inexpensive, and that's one of the key features of the system versus other flow batteries.
Okay, and I know we spoke a bit before about this regarding taking CO2
Yes.
in order to produce additional byproducts. What are these byproducts used for? Who uses them? And
Yeah.
again, I don't understand how this technology can be applied to all 4 of these applications.
Yeah, so the final area that we're working with is basically taking the same cell architecture and creating a modified electrolyzer that takes in water, takes the same cell architecture, and takes waste carbon dioxide. You can react the waste carbon dioxide with the protons and electrons from the reaction, and you can create organics from it, and formic acid and other organic acids, and you create high-value hydrocarbons, and you can do that in a distributed form to create a business model that seems to work. Right now, these organics are made at refineries, and they're shipped by barge to a deep water port, and you break bulk and ultimately send them by rail car or overland transport to an end user. And I'll give you an example. Maybe you've got a tannery that uses formic acid for processing hides to make leather. They might use a small amount of formic acid, and about 75% of the cost of that formic acid is actually in transport cost of the chemical. Instead, you can buy a unit that we would make and site it near the tannery or at the tannery, use waste carbon dioxide to feed that process, and essentially make the formic acid on site, all using a modified water electrolyzer.
So how do you see this electrochemical architectural model benefiting the industry? I mean, obviously there's a lot of different applications. What is your big vision for it, and what is your overall goal in terms of this in markets?
Yeah, we see the architecture being very flexible. It can be applied to a wide variety of things. We see it obviously fitting into these array of products. It could also fit into a water electrolysis scenario, if that makes sense. Certainly a power to gas scenario. Certainly as we go forward, filling out the fueling infrastructure is going to be critically important. We've been focused on near-term industrial applications as part of our model. The idea for us is to focus on near-term industrial applications to create a product base, and then to move forward toward energy applications as they emerge.
Are these commercial right now, or is it still on the R&D side? And if so, what is your plan in terms of commercialization, and when do you anticipate all of it?
Sure. We're in the development stage right now. We've been creating sort of a technology base for the company. We've been really focused on developing this electrochemical architecture as well as the processes themselves. We're now transitioning as a company to a product-based company. We anticipate generating products in the near future. The first product that I mentioned should become available within about 2 years. That's the hydrogen recycling product. The second set of products that I mentioned in terms of energy storage should be available in about 5 years. And the CO2 product should be available in about 6 to 8 years.
What do you see as the challenges kind of keeping this out of commercialization right now? Like, what do you need in order to bring this to a stage where it's ready to be delivered to the market?
Well, we need lots of things. Initially, obviously, we need capital to do that. We've been funded by the U.S. federal government on a variety of small business grants, and we've done very well at bringing in grants to fund our activity. We've also been funded by my funds. But those things only go so far. We are just now starting to raise equity funds to commercialize our products and have received an awful lot of interest in that regard. And so that's one thing that we need. The second thing we need is people. We're going to start hiring people shortly. We're looking for both products people as well as R&D people to bring onto our staff. The third thing that we need is relationships. We need relationships with other companies that complement what we do. Ultimately, we'll need relationships with distributors as well as universities and others.
Are you looking to get involved in more projects? I know you mentioned the Israel project with bromine. Are there any other ones that you're working on right now that might perhaps leverage some of these relationships a little more and help foster the commercialization a bit?
Yeah, we've got other projects going on right now. We've got a very interesting one going on with NASA, for example, and it's really helped to move the technology forward immensely. It's a project where NASA has a need to separate a hydrogen-helium stream. They use helium and hydrogen to test large rocket engines, and it's sort of a one-time application for NASA. But helium is
big one, though.
Yeah, it's a big deal for them. Helium is very, very expensive, and they wind up with this mixed stream of gases after they test the rocket engines. And so they don't care so much about the hydrogen, but the helium to them is very, very valuable. And so our system is being developed to deploy at their facility to do the separation. And for us, it's helped us to develop the technology, and we're building a system for them that's about 20 feet long, and we should be delivering it this summer to them.
Wow. So it sounds like your partner projects are obviously quite reputable, big names.
Yeah.
Helps out with some credibility quite a bit. Are you looking for new project partners?
We are, yeah.
If anyone here wants to get involved, how would you suggest them doing so?
Yeah, certainly contact me. Come see me afterwards. Come see our booth, which is right around the corner over here.
Booth D75, by the way, if anyone's interested.
You can also reach us on our website. It's www.sustainableinov.com. That's a good way to reach us. But we would certainly be happy to talk with you.
Okay, I'm going to maybe allow one or two questions quickly. We are running out of time here. Does anyone have any questions for Trent? Okay, well, that being said, I will thank you for being here and thank you for your time. I do have to end it because we are a bit over, but
Great.
Thank you.
Thank you so much. Thank you.